Okay, hey, welcome back. Sorry this took a while to get up. I recorded this once and the computer lost it, and it doesn't happen much that way, but it did happen. And anyway, sorry about that. I had lecture 3 up for a little while, and I will get the corrosion lecture up and very quickly after this, and then we'll get a manufacturing lecture up. And there will be some other discussion about the course generally that I'll do through written discussion too that will follow. Um, anyway, here we are. What I want to talk about is phase diagrams, and phase diagrams is really the heart of material science. It's the thing that really allows us to do to make some really careful and important predictions that really allow us to start to connect processing, structure, and properties, which is the heart of material science. We're going to focus this thing on what are called binary phase diagrams. And in a sense, this might seem advanced for high school content, but this is very accessible stuff. It's very useful if you do anything in welding or if you do anything in materials processing, heat treating. You can give your students something that I think they can really feel good about, that not that many people understand, but it isn't that difficult, and it's extremely useful. So I do encourage you to pay attention to this. And if you actually really put an hour's effort into this, you can get this absolutely, but it does take a little bit of focused effort, and I'll try to take you through this in hopefully a simple way. What I want to do is first of all kind of show that this connects pretty directly, and I'm hoping I don't lose the recording. This goes pretty directly to the content that we have in the materials camps, and in specific, in specific, the content that you learn with binary phase diagrams with the tin bismuth system. And again, this is Todd Bolenbaugh's out of Toll's Academy, his material science teacher channel out of YouTube, which I recommend highly. This is a recording that they made. This is Beth Eddy and Tom Glasgow. I can hear. Basically, this is, yeah, this is what this is, and I'm going to stand back a little bit so I don't get too much of their chatter going across mine. What this is you make a series of alloys of tin bismuth going from 0% of tin to 100% tin, and we find that in the middle we have something that melts at a much lower temperature, and we can also demonstrate this idea of a slushy zone. And it's a really, really well done lab. It works on a hot plate. The problem with a hot plate, let me turn this down. Turn that off. Okay, hopefully, yep, it keeps going. The deal with the hot plate is that it's not perfect in that you can have different temperatures at different locations, but what you should see is that the ends, which are usually pure tin, pure bismuth, you put on the ends are going to melt a lot later than the stuff in the middle. The first one to melt should be eutectic, which we'll talk about. And then between the eutectics, you should see these persistent slushy zones. And here you see Beth poking at a slushy sample. And I'll talk about what that is. It's a beautiful experiment, works very easily, very low cost, and there is a lot to this. And we could easily augment this with microstructures and so forth if you like as well. So let's go back to the slides. And again, that's out there. And oops, we'll continue with this. And I was just looking to make sure there's something that's beeping that indicates I'm still recording. Yep, it shows. So stop recording means I'm still recording, which is a good thing. I want to do this again. So anyway, lecture 4 is phase diagrams, and we'll go through the key things we want to get a couple of times here. So learning objectives here. Go back. Learning objectives for this unit. I hope to teach you to be able to teach your students, first of all, what is a phase diagram, and what we're going to talk about is a phase diagram of a specific type, binary phase diagram, and this is a specific type of binary phase diagram is a temperature composition phase diagram. This is by far the most commonly used type of phase diagram in material science. And with this, we're going to learn three important things that we can get out of a phase diagram. The first one is if we know what the overall composition is, we know what the temperature is, we can say how many phases we will have at a given temperature composition point. The second thing we can say is we can tell you what the composition of each phase is going to be. And the third major thing that we can tell you exactly is what volume fraction of each phase you expect to get. And then with a little interpretation, we can also tell you how the solidification process is really related to the structure that you end up getting. And this is where it really becomes very, very powerful. The big limitation on all of this, those of you who are chemistry teachers understand the idea of thermodynamics very well. Thermodynamics tells you this is what you expect. This is the lowest energy state. And all these phase diagrams are based on the idea that we're moving towards thermodynamic equilibrium. And that the idea there is that we are heading towards some kind of an energetic ground state. We don't always get there, but we're usually pretty close. So, and for the reason that we're usually pretty close, these phase diagrams are really, really very, very predictive. Okay. So let's march forward. So this is the system that we very commonly use in the ASM materials camp sequence, and the ones that we'll show you are walk through the system. Just change my ink color a little bit. So this is bismuth tin system, and we've got temperature on this axis, and we have basically the percent of tin on this axis going from 0 tin, meaning all bismuth on this side over here, to all tin over here, going from 0 to 100%. This is done in a mole fraction basis. You can also do this in a weight percent basis. Again, one of those classic chemistry conversions, go from mole percent to weight percent you can do with this, and that all fits on the phase diagram. Okay, now just to steal the thunder, I'm going to go through this again more carefully as we go, but I want to label the phases here, and let's just pretend that nothing happens beneath this temperature. It gets a little complicated beneath this, and this is a little bit anomalous, at least for a first teaching thing, so don't worry about that. Certainly, if you take either of these elements hot enough or mix them and get them hot enough, you develop liquid. And this would be over here a pure bismuth liquid. This would be a pure tin liquid. Over here you've got a mixed liquid, just like a two-component system. Mix them up, you get a liquid that consists of bismuth and tin both together. Okay, so now the other the other single phase regions you have here, this is basically a bismuth rich, and this is a tin rich metal, and they're basically single phase, meaning you've got one crystal structure there, and we'll talk about what phases mean in a little bit more carefully a little bit later on, but basically it's pure bismuth crystals here, pure tin crystals here, and you can have a little bit of bismuth in the tin over here, and you can have a little bit of tin in the bismuth over here, and you can see in this case that you can get about 3 or 4% tin in the bismuth solid solution here. Okay, the next thing are two-phase regions, and we've got, and single-phase regions are always separated by two-phase regions. It's one of the fundamental rules of phase diagrams. So this is bismuth solid plus liquid. This is tin solid plus liquid. And here's bismuth rich plus tin rich solids across here. Those are two-phase regions, and you'll see pictures of those. And this all really correlates very nicely to what you just learned in the last lecture about metallography, so we can actually look at these structures, and that's actually quite interesting. Okay, let's march forward. So again, with the idea of phase diagrams, the key question we're really trying to answer is that when we combine elements, we want to say what is the equilibrium structure, and I mentioned this idea of equilibrium being an important one. It's the end point that we think things would get to if we leave them at moderate temperatures for a long time and allow diffusion to happen. It's not always easy to get there. And with this, you see two distinct phases here, and the two distinct phases that we end up seeing, this one we're calling phase A, which in this case we're considering aluminum plus copper. You can see this is aluminum with copper mixed into it, and this is what we would call a solid solution. And then you see this region here, this is ordered. It's clearly different. That's different crystal structure. And because it's physically distinct, and you can see the way this crystal is, you can see they're lined up this way to have different properties in this direction than you would in that direction. We call that a separate phase. We'll call that phase B. So in this case, you see this is two-phase. And you also see, and we'll define this in a moment, this is also two-component. Okay. So again, going back to the key questions we're going to answer, how many phases do we get? We see there's two in this picture. We'll see that in the phase diagram. What's the composition of each phase? Well, you can see on mole fraction, this thing here is 50-50. You've got one aluminum atom for one copper atom. Here it's dominated by aluminum atoms. What does that look like? Maybe 80% copper, 20% aluminum. And then also you ask the question, how much of each phase do you get? In this case, you see this is the only region of phase B. So yeah, this may be about 10%, 15% phase B, the rest of it phase A. And if you're describing a microstructure, those are some of the key questions that you'd really like to be able to answer. So let's talk about just basic terms here. So in the last thing we had aluminum copper system. Those are the two components. So components represent the elements or compounds that are mixed together. So for example, we could do aluminum silicon would be a two-component system, and that's based on elements. We could also do, for example, water plus sodium chloride, one that you can easily do in your kitchen. And actually there are some nice useful demos you could even do with that in a class setting, and these would both be examples of two-component systems. And as you can imagine, most real engineering alloys have many more than two components in them, but if you understand the two-component system well, it's not a very big jump to go to higher order systems. Again, it's not a very big jump in a sense, but it's well beyond what we're going to do in the context of this class. Okay, the next definition is phases. Phases are physically and chemically distinct regions that result from mixture. And going back, to the last thing, you see these are different phases we're talking about. These are distinct regions. This is a disordered solid solution. That's the ordered region. Those are phases because they're physically distinct from one another. And then composition we talked about last slide also. It's basically how much of each component is in each phase. Okay, so this is again an aluminum copper alloy. This lighter phase is aluminum rich, still contains copper. And then we have this darker phase, which is copper rich, which also contains some aluminum. Okay, so it doesn't mean that these things are pure, but they're distinct from one another, and you can see that they're distinct. You could measure hardness, density, any number of properties, and see that they're distinct from one another. Okay, so let's consider a really simple system, one that indeed you could easily study in your classroom or your kitchen or outside on the road on a winter day. This is the ice-salt system. We can, for almost any two-component system, develop a phase diagram for it. So again, we have the horizontal axis is composition, and composition going from pure water over here to sodium chloride over here, and then we've got temperature going this way. For those of you that are chemistry teachers, you've probably seen pressure temperature phase diagrams. We can do this for single component systems, but this is same concept, but a little bit different. Okay, so let's look at the solubility limits. And solubility limits is a max concentration for which only a solution, meaning a single phase region, this is kind of code for single phase, is present. So the single phase regions on here, this is brine. This is basically a liquid, just salt water is another name for that. Along here, there's another single phase region that has very little solubility, but this would be just pure ice. Ice can dissolve very little sodium chloride in it. And then these single phase regions are separated by two phase regions. So this is ice plus brine. This is a salty glass of ice water. Down here you have ice plus this sodium chloride water compound. And you've got brine plus that compound, and that's your phase diagram that you'd end up getting. Okay, again, just demonstrating this phase diagram is actually a little bit complicated, but it demonstrates the point that we can do phase diagrams for these compounds as well. Okay. So what we can do is we can see that temperature and composition both change the number of phases present. So here what I can do is sit here at point A, and A is a salty glass of ice water, ice plus brine. What I can do is I can go from this two-phase region, heat it up to a single-phase region, add heat energy to it, and that takes me to a single-phase region. I could also imagine adding more salt to it, just like a 8-year-old sitting at a Denny's table. They somehow seem to want to put salt in the water. It's sort of the same thing, and you see that you can actually just, if you put enough salt in, you will melt the ice, and that's part of why we put salt on roads, right? So the other thing that you get from this is you can see that if I know what my compositions are and what my temperature, I'll pick any old spot on here. Maybe I'll pick that spot for fun. You see I've got a two-phase region, and I know what those two phases are. Those two phases are ice and brine. So that's the first kind of big learning objective. We know that if we have a phase diagram, we can say what the components are. How many phases are there, rather. So now let's start considering metallic systems. Let's consider a simple solid solution. This is a nickel-copper solution. Nickel and copper are fairly similar elements from our point of view. They both like to crystallize in the face-centered cubic structure. They have similar electronegativity, and they also have very similar atomic radii. And for those reasons, and there's some rules put together by a guy named Hume Rothery many years ago, and he says that things that have the same crystal structure, same electronegativity, and similar crystal size, they should form extensive solid solutions with one another. And indeed they do, and we can show that on a phase diagram. So here is a phase diagram, about the simplest one you can get for a real metallic system. This is the copper nickel system. Pure copper on this axis, pure nickel on this axis. So for pure copper, melts here at a little less than 1100 degrees C. Pure nickel melts at about 1400 degrees C. We can bring and we can make a solution to them. If we melt them together, we see that we can get single phase liquid. Also, if we go down to a low temperature down here, we get what's called a solid solution, meaning you've just got mixed a face-centered cubic crystal that on some sites has copper, on some sites it has nickel, and the proportion of copper or nickel being on any site is basically just the proportion, just the probability, just the mole fraction of each one. Okay, so again, we've got our two single phase regions, liquid being a single phase region, face-centered cubic solid being another single phase region. And we've got three phase fields, meaning the liquid phase field, the solid solution phase field, and then single phase regions are always separated by two phase regions, liquid plus alpha being the two phase region in between. So again, this is a binary system, got two independent variables, temperature and composition. We as material scientists don't consider pressure typically as a free variable most of the time. We usually do all our work at atmospheric pressure, so we're assuming everything happens at one atmosphere. And in this system, it's isomorphous, one morphology, being phase 100 cubic, only one solid phase. There's complete solid solubility of one in the other. Okay? Simple as pie, I hope. So rules of phase diagrams. First one we've already seen. First rule of phase diagrams, we know temperature and composition. We know the number and types of phases that are present. So let's imagine point A we'll put on the map would be 60% nickel and 1100 degrees C. So here's 60%, and this could be weight or diagram should specify whether it's weight or atom fraction. And 1100 degrees C, point sits right there. What do we have there? I'll wait for it. Anyone? Anyone? I'll tell you. So it's single phase phase center cubic. Second case, excuse me. Second case is 1250 sitting here, and 35 weight percent, 35% nickel, which would sit, here's 30, 35 sits about here, 1150. That's intended to sit about right there. And that would be two phases, liquid plus solid. So okay, so now this sets up the next questions that we want to answer is what's the composition of each phase, how much nickel and how much copper is involved in each phase, and then it also sets up the question of how much of each phase is there, and we'll get to those in due course. Okay, so phase diagrams, second thing we want to know is the composition of each phase. And it turns out, so this is the liquid region. This shows you how much nickel you can put into the copper before it stops being single phase. It's a solubility limit. All you chemistry teachers are well aware of solubility limits. So it turns out what you have is if you've got this point here, which is 35% nickel and 1150 degrees, 1250 degrees C, whatever that was, looks like 1250 in that case. That's our composition point. And then we can draw a line, basically a constant temperature, because all the phases are a constant temperature that connects this liquid phase and the solid phase. And this is representing the solubility limits of each phase. Those 3 points are tied together by something called a tie line. So to add a little bit more vocabulary yet, this tie line is a constant temperature line that ties together this thing we call the liquidus, which is the solubility limit in the liquid, and the solidus, which is the solubility limit in the solid, ties those together. So what you have is this composition of liquid in equilibrium with that composition of solid. Okay, so just to work through this, just to work through the example here on the side. So at temperature T sub A, you've got only liquid, and the composition of the liquid is 35% nickel. At T sub D, again, you've got a single solid solution. It's a crystal instead of a liquid, but again, each lattice point is governed by just the probability of the material being of probability of each lattice point being occupied by a copper or nickel atom is just simply the mole fraction of each in the solid. And again, solid solution, 35% nickel. And now here at T sub B, the composition of the liquid It's a composition at the liquidus, which if we go down here is maybe, about 31% nickel. And the composition of the solid is out here, at about 43% nickel. And of course, there has to be overall conservation of mass and so forth. So as a result of that, the closer this overall composition point is to the liquidus, the more liquid you're going to have. The closer this overall composition point is to the solidus, the more solid you're going to have. I'm just going to leave that out there for now, sort of as foreshadowing, but we're going to get back to that and put a real quantitative rule behind that in a little bit. So, and now I'll give you the foreshadowings over. We'll turn this into weight fractions of the phases that we have. And this is the third rule of phase diagrams. If we know the temperature, we know the overall composition, then we know the relative amounts we have of each phase. This is something called the lever rule. And again, as I said, if this point gets really close to the liquidus, there's no reason there should be much solid in it. If that point gets really close over here to the solidus, there should be very little solid in it. But what's really interesting here, and the overall composition doesn't change the compositions of the saturated solid and the saturated liquid. So those compositions don't change. You're simply changing the relative amounts of each one that you have. Okay. Okay, so at T sub A, it's only liquid, T sub B is only solid. In between, it's something in between. And then what you have is a weighted average in between where it's basically like a lever. So what I can do is we can see, is this point here, I've said it already, but I'll let you think about it again. Is this point going to be mostly liquid or mostly solid? It's going to be mostly liquid. And so the weight fraction liquid turns out by this lever rule, and I'm not going to show you how to derive it in the next slide, but by this lever rule is going to be this fraction over this total fraction. So basically this distance S over R plus S represents the fraction of liquid, and that's basically composition of alpha minus the overall composition over the entire length of that lever, which is composition of alpha minus composition of liquid. And in that case, that's going to be, about 70% liquid or so. And then the weight percent solid is going to be length R over R plus S. That's going to be about 30%. And of course, those two fractions should add right to 100%, and they do. Okay, and they do here on the graph as well. Okay, we can do a proof for this, and I will leave this to you if you're so inclined to do this in your class. It's not very difficult. The two things that we really care about, we always know that the sum of the weight fractions, the weight fraction of the solid plus the weight fraction of the liquid has to equal to 1, or for a more general system, you can say weight fraction of alpha plus weight fraction of beta has to sum to 1. Like a 70% plus 30% equals 100%. And the other thing, you have to have a conservation of mass for each phase. So what you can do is say the weight fraction of alpha multiplied by the composition of alpha plus the weight fraction of liquid plus composition of liquid has to equal to the overall composition. So for example, if I've got something that I know is 10% nickel, and it's most of it is alpha, you know that nickel has to partition among those things. Okay. So when we do that, we end up getting this, where we get the weight fraction of liquid is S over R plus S, and this is R over R plus S gives you the weight fraction of liquid in alpha. And that looks a lot like a lever, and so that's why we call this the lever rule here. That's basically all this is. So the closer the fulcrum gets to this side, the more the heavier that side has to be to make it all work. Or actually, sorry, the heavier this side has to be. So you have more liquid the closer that comes to that point. Just like we talked about, as the composition point becomes closer to the solubility limit, you're going to have more and more of that stuff. Okay. And in the homework problems, you will get a chance to try this out momentarily. So now let's talk about how this starts to relate to processing, and that's where it really kind of gets fun for we material scientists. So let's again consider a copper nickel alloy. We got to cool down, and we start from all liquid. We hit this point B, we start forming our first solid. So all liquid up there, point B, start forming a little bit of solid, and it's going to be 34 weight percent nickel in the liquid, 46% in the solid. Cool down, we end up seeing that the equilibrium compositions change. Also, the amount of solid increases as you decrease in temperature. And as we continue to cool down further, we are almost entirely solid at this point. There's actually more solid than indicated here. And again, the compositions are shifting. And then when you get all the way down, we expect to see just again a single simple solid solution. In reality, the elements can't move around that easily, so once you start forming this, you kind of tend to lock stuff into the solid, and it isn't able to diffuse so easily, so you don't always end up here at the lowest temperature with something that's completely uniform. But again, it's a pretty good approximation. So what we talked about before, we talked about equilibrium as a way we think phase diagrams work. And so if there's a lot of diffusion, you get no gradient, and at the last temperature you'd end up seeing something that's compositionally uniform that looks like that. But in real life, we know that the first solid to solidify is the solid usually that has a higher melting point. It's the nickel solidifies first. So you get a core that's really rich in nickel in an outer region that's not so rich in nickel. And so this is what you see in real microstructures. If you look at solidification structures, and again, if you really do material science, there's a lot of great stuff available just on the web, a lot of great microstructures that show what these look like. You see dendrites, cord structures, you see all this kind of interesting stuff that we really do see in real welds and brazes and cast structures and all of that. And this all does have technical importance. So this is kind of the simple-minded thing. This is really what we get. And anyway, the phase diagram still gives you a lot of information to understand that, even if you don't get everything. So now what I want to do is make things a little bit more complicated, talk about binary eutectic systems. And the definition of a eutectic is a point where you've got liquid going to a solid phase alpha plus another solid phase beta, and that's our primary definition of a eutectic. Okay, so here we got the same sort of thing. We've got single phase regions, liquid, alpha, and beta, and this is exactly what you see in the copper-silver system, which is the sterling silver system. And here you've got a eutectic point where a temperature just above this, you can see the phase diagram says it's completely liquid. A temperature just below this, it says that you end up with a two-phase structure, alpha and beta. So what you end up seeing are two regions of limited solubility. Alpha can dissolve 8% silver in copper. And on the other side, you can get up to about 9% copper in silver. And that's actually what we end up doing with, I think that's sterling silver. That's I think sterling silver, you put a little bit of silver in there. I should have looked this up in advance. But the idea is it still has its luster, still has its corrosion resistance, and by putting a little bit of copper in the silver, you get much, much better strength. So that's why we do it. So these eutectic temperature is the lowest temperature, which is a liquid. And again, this is something, if you do this, the hot plate demonstration, that comes right out. And again, this is our eutectic definition here. Okay, so now what we're going to do over the next few slides is show how this plays out into some real systems. This is another classical system. This is the lead tin eutectic system. And what we end up seeing here is, let's just go right to this point here. At this point, the composition of alpha, this is pure lead here, pure tin over here. You're going to have about 10%, and about 10% tin and lead. The other phase, the beta phase, you're getting is going to be about 2% or so tin, or rather lead, P, V, and SN. And the relative amounts of each phase, if you do this, again, relative amounts, first of all, it's going to be more alpha or more beta. Give you a second to think about that. Okay, this phase point, this composition point, is closer to the alpha side. It's going to be more alpha than beta. And if you look at this, you do this, call this R, call this S. It's going to be R over R plus S. And oh, by my eye, that's going to be about 60% by weight alpha. And then beta is going to be S over R plus S, which is going to be 40%. Of course, they have to add to 100%. Okay, so that's what the phase diagram tells us we are going to get. So let's now consider what we get with microstructures with these materials. This is a system. Again, we've got lead with tin. Let's consider we just got 2% here, and consider the different locations here. At the highest temperature, it's all liquid. Here we start to solidify. Here we've just got something that's completely solidified, and that persists all the way down. Okay, all the way down, you see that as low as you go. So the result, ultimately, when you cool all the way down, is a single phase solid solution. So now let's consider something that's a little bit more interesting, and this is a really important thing. If you've ever heard about age hardening or precipitation hardening, this is the way that aircraft aluminum alloys work, is on age hardening or precipitation hardening. But again, we're going to look at this in the lead tin system, but the same sort of thing happens. So what we end up seeing at the highest temperature is it's all liquid plus alpha here, and again, we could draw a tie line in there if you like. This is the composition of the liquid, that's the composition of the solid. It can be about 50-50 of each. If you go to this temperature, let it sit for a long time or some time to let it equilibrate. It should be all one phase, one composition. Cool further, you get a two-phase structure where you should see something that's basically alpha that has beta in it. And the morphology depends very much on how fast you cool it and what you do. And if you're going to do age hardening or precipitation hardening, what you do is you end up quenching to a low temperature, giving you a non-equilibrium, what we call a supersaturated solid solution, and then you cool back, or then you heat back up to some modest temperature, and that lets this come closer to thermodynamic equilibrium. It allows diffusion to happen and starts giving you these small particles in there. if you just cool slowly through this, diffusion is easy, and the beta particles want to form where it's easiest to form, and they'll usually form along grain boundaries, these intercrystalline boundaries you heard about before. That gives you a lousy structure, basically. We like these small little beta particles in the alpha matrix, and so we usually quench and age, and that's how we do age hardening and precipitation hardening. It's a real short summary of how we do things, but it's basically correct, and there's more to it, but not a massive amount more to it. So here's microstructures and eutectics continuing on. Again, let's consider an initial eutectic composition. Again, if we cool down, diffusion is important here. Over a very short temperature range, you're going from liquid to a two-phase solid. So you've got this liquid here, which is basically lead and tin. Then in the end, you've got to make a two-phase system out of that. And so the atoms physically have to move apart from one another. And that's going to happen by diffusion. So you're going to have the tin-rich phase lining up here. The, let me see, maybe it's the wrong way. We're calling the alpha as being the lead-rich phase. So alpha, this would be lead-rich. This would be tin-rich. So as the lead comes over here, it's going to diffuse in the liquid because it's being gobbled up. It's sucked up over here. The tin is sucked up over here, and you end up growing these plate-like structures, and they're small close together because diffusion won't let the atoms move terribly long distances. And it turns out the faster the cooling rate, the shorter those distances are. So we end up having really primary control over what happens based on the cooling rate. And then this is what a real microstructure might look like. You're getting these platelets that form, and depending on how you angle through these platelets, you see different representations of that as you go through. Okay, so that's eutectic solidification. Gives you these structures, and if you Google up eutectic solidification structures, you'll see all kinds of cool structures that look something like that. So there's your liquid, cool down, you end up seeing the cartoon that looks like that. So let's consider what happens for off-eutectic solidification. Here's what we see happening at the highest temperature. You've got all liquid. This modest temperature, again, this is solidus line, this is liquidus line. You can put a tie line through that, figure out all those things we did before. Same tie line idea works just above the eutectic temperature. And in this case, what you've got is the composition of alpha here is going to be about 18.3% tin. Again, lead. The composition of the liquid is going to be just above this at about 61%. And then the weight percent alpha is going to be this R above the line over S above the line, and that's a little closer to eutectic, so you're going to have a little bit more liquid than solid, so you're going to have maybe about, again, it's going to be R over R plus S, and that's going to end up giving you something of just making sure I'm doing this right. So we're asking the question of how much alpha is there, and again, the more alpha you have, the closer you're going to be to this side. So correctly, it's going to be, if we're over here, we're entirely liquid. Over here, we're entirely solid. So the fraction of alpha that we're going to get is C naught minus CL. It can be S over R plus S, which is going to be about 30% or so, and about 70% liquid. And then when we get beneath this thing, again, it's going to be this composition of alpha in equilibrium with that composition of beta. And then, so what we're going to have is we're going to have about 18% tin in the alpha. You're going to have about 2% lead in tin. And then the weight percent alpha is going to be these things. I'm going to call this R prime, S prime. And the weight fraction of alpha you're going to get here is you're going to be predominantly alpha. You're closer to that than this. So it's going to be S over R plus S. And you're going to be about, in this case, 70% alpha, 30% beta. Okay, and so when we look through that, you'll see that where these alpha particles you made persist, and then the liquid turns to eutectic, so you see these particles in a eutectic matrix. Okay, and we'll show some pictures of that here in a second. So that's what you end up seeing. This is our eutectic. Things to the left of this we consider hypoeutectic. And it depends a little bit on the definition of what you call, but again, this is lead and tin. If we would draw the diagram the other way, we'd have change our hypo and hyper. If you have more solute than eutectic, we call this hyper eutectic. And either way, so what you see is the physics is the same. So at the eutectic point, you see just a simple eutectic solidification. On the lead-rich side, you form these lead-rich particles first. That's what you see here. On the tin-rich side, you form the tin-rich particles first. And again, these are all nice examples of metallography down here where we cut, polish, etch, as we talked about before. And so you can understand these microstructures. And again, this is simple stuff that is really incredibly powerful, and we use it all the time in material science. So iron-carbon phase diagram is another really important one. There's two important points here. This is eutectic here. And here you've got liquid goes to alpha plus beta. And here you've got a eutectoid. A eutectoid is where you've got solid 1 goes to alpha plus beta. And the solid that we're talking about in this case is this particular austenite transformation. And I don't want to go through this too much here. I think for fear of starting to go through too much material, all the same ideas apply. But there's two really important regions in here. First of all, there's a region in here, in this composition on down is what we call cast irons. And here we don't tend to see so much of the cementite. We see more graphite forming in that. And then this austenite is basically the basis for steels. And typically we sit here below about below actually about this 0.8% carbon, because you can tend to make things that are brittle. You get out beneath that. But by taking this austenite phase and controlling the cooling rate, you can either get this phase that we call perlite, or the structure that we call perlite, which is a mixture here of iron, and then these black stripy things you see are iron carbide. If you cool fast enough, you'll get something called martensite, which is much harder and somewhat brittle. And there's a whole range of properties you can get from this. And that's the reason we use steel so much, because we can get all these wonderful properties out of steel, all again based on this phase diagram, which is really a little difficult but pretty accessible, I'd like to say. Okay, I want to end the lecture on kind of maybe two kind of fun things. And just show that you can have systems that have very dissimilar melting points. This is an aluminum gallium system. This is pure aluminum here, pure gallium over here. And you see you have this eutectic temperature in Kelvin that's right around room temperature. Gallium is liquid at room temperature, near liquid. And so what this does, you get this eutectic down here at room temperature. And what you can do is if you take, we know that aluminum is made up of these crystals that end up popping together like this, that fill space. And if I take this, imagine this is aluminum down here, put a little dollop of gallium, let me Since I have the colors, I might as well use the colors. Imagine I take a dollop of gallium over here. We can see that these things want to form sort of a two-phase structure, aluminum plus gallium, and the way it ends up happening is the gallium can diffuse down these grain boundaries like this, intercrystalline boundaries, and give you basically gallium-rich regions throughout all of this. Having a liquid at your grain boundaries is something that will really weaken them, and what will then happen is this is something called liquid metal embrittlement. And so this is a liquid metal embrittled surface. And what's kind of nice about this picture, I also put it up because these are what the individual crystals look like within the aluminum structure. Those are the individual grains. And this doesn't show a micron marker, but usually one grain is about 30 microns or so. So maybe that's about a 30 micron marker would look like that. And that's what this liquid metal embrittled structure looks like. And these are all these crystals come together to fill space, which I think is always kind of cool. It's like these little dodecahedron sorts of shapes that all fit together and fill space. The other thing that's important about this is it can be a very potent way to embrittle stuff. And that has been used. Mercury will do some sort of the same thing. There's rumors out there, I think there's some stories that we did this to a German aircraft in World War II and could embrittle their aluminum by putting mercury on it, and we had people doing that in kind of covert ways, and wings would snap off and so forth. And anyway, just kind of a fun thing to end the lecture on, and you can see some more detail on that in the link. So in summary, phase diagrams are the heart of material science. With those, we can tell you the number and types of phases, weight percent of each, composition of each phase, and all we need to know is the temperature and overall composition. What we can talk about, and later we're going to couple this to alloy to talk about how we can use this to change tensile strength and ductility. And I've also told you about eutectics. Eutectic is basically liquid goes to alpha plus beta. And eutectoid, where you got one solid phase we'll call gamma, goes to some other phases, alpha plus beta, and that gives you a whole range of microstructures. And by changing things like solidification rates, transformation rates, cooling rates, you can get a whole wide variety of structures and properties, and that's again the heart of what we do. Feel free to ask me any questions either through phone, email, and I apologize for the time it took to get this up, but